In this part, we'll be discussing the engines that SpaceX uses, the actual rocket motors that are used on both the Falcon 9, the Falcon Heavy, and eventually the BFR, or as it has recently come to be known, the Starship and Super Heavy booster. We'll quickly discuss what these engines have to do and the sort of specific design requirements that they are subject to when it comes to reusable systems, and the way that SpaceX intends to use these either many times or only once. We'll look at specifically two engines, the ones that SpaceX are currently using and developing, the two most interesting of these engines, which will be the Merlin engine and the Raptor engine. The rockets are similar and different at the same time, and yet they both fulfill very similar design requirements, and it's quite interesting in many ways to compare and contrast how these different motors achieve those requirements. First up, we need to discuss what these requirements are. What do these engines have to do? In short, these rocket motors, obviously the rocket has a long way to go, but these rocket motors specifically are on the first stage. We'll only be discussing the first stage part because that is the reusable part as it stands today. They are the part that launches off the pad, so they need to be powerful enough to lift the whole rocket, payload, fairing, fuel and everything off the pad at launch. So first up, they need to be powerful. Then they need to fly for a long period of time, over 2 minutes, to the point where the first stage's fuel is almost expended. So they also need to be reasonably reliable, and they need to work together, as on the Falcon 9 there are 9 engines, and on the BFR rocket, I will refer to it as the BFR rather than the official name because BFR is more commonly used at this point. Anyway, on the Falcon 9 and the BFR, they have many, many engines, so they also need to be able to work together. So they need to be powerful, they need to work together, and of course they need to be efficient to both save costs and to get more fuel. They also need to be reliable, of course, because reliability is key. Because if you reuse these engines 50 times, they can't have a 1 in 50 chance of failure. That is simply too high. So there's something else that happens after that main engine cutoff. There are 3 times the engines need to be ignited after that. The entry burn, or the re-entry burn, if you want, the boost back burn, and the landing burn. So those are the last 3 burns, and if you count the ignition at the very beginning of the launch, there are 4 ignitions that these engines need to go through. So, not only do they need to be powerful, reliable, and work together, they also need to have at least 4 ignitions before they need to be restocked by the ground, which is a major design challenge. Actually, that's an interesting thought, don't you think? If we are landing these rockets on let's say a big boat, a drone ship, or a landing pad, they need to be throttleable engines, because if your engine is too powerful, the rocket might stop slowing down and start going back up again. So the engines need to be throttleable and controllable as well, which is, all in all, a very large number of requirements. These need to be very, very specific systems. The first one we'll talk about is the Falcon 9, the Merlin engine. Now there are 9 of these on the base of a Falcon 9, arranged in an octaweb format with 8 around the outside and 1 in the middle. Pretty simple. They are an open cycle LOX RP1 engine. Essentially, the fuel is pumped into the main combustion chamber by another little combustion chamber that burns a little bit of fuel, which powers the pumps, which pumps loads of fuel very fast into the main combustion chamber. This is called a turbo pump. It's essentially a tiny little rocket engine powering the pumps that power the rocket engine. Open cycle means that the exhaust from that turbo pump goes as an exhaust. It gets shot out the side and is not really contributing. It's wasted fuel, essentially. But it makes these engines simpler, much simpler. So, it is an LOX RP1, which I'm sure we've talked about this before, liquid oxygen, and RP1 is kerosene. So really, kerosene and oxygen engine. Very basic fuel, has some problems, but we've discussed them in the past, and the Merlin manages to have very few problems with this particular fuel. Also, importantly, I'm going to discuss something incredible about the Merlin engine, which is the pintle injector. You go, wow, what's a pintle injector? That sounds fancy science words. Ugh. Well, a pintle injector is a form of injector rather than simply creating a gigantic hose and sticking it into the combustion chamber. Well, if you did that, then the combustion chamber would happen all the way up the hose and into the engine. So you need some kind of way to inject this fuel from your pipe into your engine without the fire from the engine going back up the pipes and into your fuel tanks. So most, or I suppose many common rocket engines use a shower head injector. When I say shower head injector, it is actually literally a shower head. They pump both fuels into what is a shower head and it just gets spread into the engine, which is good. But have you ever turned your shower on very low? It sort of dribbles out. Not great. So if you're turning your engine to a very low degree, you don't want that dribbling to happen. Otherwise, stuff will start to combust right on the head, and then it will start to combust in the pipes, and then it will start to combust in the fuel tanks, and there goes your rocket. But SpaceX solves this really well. They don't use a shower head injector. They use a pintle injector. This is a pintle injector, shown from the side. You see, the fuel comes in the middle, and it is limited by the amount of oxygen coming in, which means if you pour a load of oxygen in here, it's going to open up the valve and allow more fuel in. But that means to control the fuel and oxygen, all you have to control is the amount of oxygen coming through. And that's just a single valve. That's why that is the huge strength of this pintle injector, is that if you can turn down your liquid oxygen input valve, then you can also at the same time decrease the amount of fuel coming in addition to the amount of oxygen coming in. So it's a clever solution, and you also don't get that annoying dribble at the end, which is very important because the Merlin engines need to be controllable. They need to be slow and controllable. The Merlin engine, remember how I mentioned that it requires 4 ignitions, which is a load of ignitions. It uses TEA, TEB. We've talked about this before, but I'd like to go into it in a little bit further depth. TEA, TEB are both liquids, triethyl aluminium and triethyl borane. I personally alleviate this to TTEB, but I'm not sure if that's a very technical way of talking about it. Anyway, TTEB is a pyrophoric liquid, but it is a pyrophoric mixture, which means that on a contact with air at around room temperature, it will ignite. And so if you have enough TTEB, you can always ignite your engine. Just put a little bit in there, and it will touch the air and go boom. And TEA, triethyl aluminium, is especially good at this because it will also ignite on contact with liquid oxygen, cryogenic oxygen, so super cold oxygen for rocket use. So it's often used to ignite rocket engines. And the Falcon 9 has a bunch of it on board so that it can ignite its engines up to 4 times. The third thing I'd like to talk about in this part, the second engine, is the Raptor engine. An engine that has never actually flown yet, except it's such an amazing, a remarkable idea. And apparently SpaceX have been testing it for almost 3 or 4 years now. So it should be going really well soon. It is the main engine for the BFR, the main booster for the BFR. And the Starship, actually, big spaceship. This Raptor engine has to obviously be very coordinated with its friends, because if you don't know, the BFR will have, I think, 42 engines on its first stage, and this rocket will do the same as the Falcon 9. It will launch up, deliver its payload to space, and then come back down and land at the launch pad. This engine is a little bit different. It is a closed-cycle methalox engine. And so, methalox is a lot like LOX/RP1. We say methalox. It is a shortening of methane and liquid oxygen. Liquid oxygen becomes LOX. Liquid methane becomes just metha. So we combine those two together and we get a methalox engine, which is a really cool name. But it is closed cycle. So you remember what I said about the Merlin engine? Its exhaust just goes whee, just leaves. The exhaust from the turbo pump just goes and gets pointed out the end. It doesn't go into the combustion chamber. It is effectively wasted fuel. Now, it's not a lot of wasted fuel, but it is still wasted fuel. And when it comes to rocket engines, wasting fuel is really bad. So, the Raptor engine says, okay, that's cool. So they take the exhaust and they plug it back into the main combustion chamber. It's not that simple. It's rocket science to get this back together. Because where the ignition happens, we call it the pre-burner, to power the turbopump. That is a lot cooler, because this is a little bit of fuel, remember? That's powering these pumps. So that is not quite as hot as the main combustion chamber. So if you piped this exhaust back into the main combustion chamber, it would explode. The heat from the main combustion chamber would work its way back up to the turbopump. The turbopump would freak out. It wouldn't be used to this much heat, this much fuel. The pressure would be way too high, and the engine would just explode. So I believe it operates using two pre-burners with a fuel-rich and then an oxidizer-rich side, which come together in the main combustion chamber. It is much more complex than the Merlin, but it is much more efficient. This closed cycle makes it a little bit more complex, but it provides a gigantic boost in efficiency over the Merlin engine. And this is incredibly useful for a rocket that is designed to possibly go to Mars and to have regular launches to Earth orbit. That is incredibly important and an incredibly valuable trait. So closed cycle engines are very good. And the way that the Raptor is designed with this system in mind gives it a very high fuel flow, which means they can greatly increase the speed that the fuel comes out of the end of the engine. So the heated up gases combine, burn together, and gets blasted out the back. And in the Raptor engine, this happens very, very fast. I'm not going to talk about the rocket equation, which is a bit complex and possibly not important as to what we're talking about here. But it essentially states that the amount of distance you can get your rocket to go is directly proportional to the velocity of your exhaust, VE, exhaust velocity of the hot gases coming straight out of your engine. Those are the other two main things that make the Raptor a bit superior to the Merlin, but it also has TEA-TEB ignition. It has this T-tab as well, which SpaceX have clearly noticed is quite a phenomenal way to ignite your engines. So they are using a similar thing on the Raptor engine, which makes the engines look spectacular, because when they start up, they have the green flash of the T-tab, and then Methalox burns pinkish, purplish, and very white hot in the middle. So those are the three things I was talking about: what the engines need to do, how they work, some stuff about them, some more ignition-y stuff, and a closed cycle turbo pump. I'm simply talking about this because these are very cool and sort of more of an introduction to these complex rocket systems that I'd like to mention. That's really all for this part. In the next part, we'll be talking more about SpaceX and just sort of polishing off our understanding of what they do and how they do it so damn well. So I'll see you then.